Okay, so today we are basically do a quick overview of another method of parameter estimation, which is the method of least square. So we are going to discuss that. So today we are going to uh, discuss the method of least squares. Okay. Now, when is this thing applicable? Like, what is the statement of the problem? If you see such kind of problem, then you think about method of least squares. So when it is applicable. So suppose you are measuring quantity, which is y. So this is the thing that you are measuring. So this is measured, and this y is theoretically given as a function of some other another random variable x. Okay, so this y is a function of another random variable x, and this functional dependence. Uh, it also depends on some unknown parameters. Let's say theta. So I write theta vector as a collective term. So there are different thetas uh, that connect these things. Okay, and you measure these y's with along with the statistical uncertainties. Okay, and at different values of this x. Okay, so we measured y along with the uncertainties, along with the uncertainties uh, at different values of x. Okay, so so these points, so the different values of x are known. So I call it x1, x2, let's say up to xn. Okay, and the corresponding values for this y that you measure are basically y1, y2, dot dot up to yn, and these these you also measure the statistical uncertainties in them as well. So uh, let me call them, let's say, plus minus sigma 1, plus minus sigma 2, and so on. So there are certain things that you basically measure. Now the question is, how do you measure these y's at different values of x? I will give you a typical example of this. So a typical example is that suppose you are measuring the heat flow through a metal rod. Okay, suppose this is a metal rod. Okay, and you are hitting this end, and you want to know the heat conduction along the length of the rod, and you have a scale attached to it. Okay. Suppose this is my centimeter scale that is attached to it. This is 1, this is 2, and 3. These are in centimeters, let's say. Okay, and at these locations, certain thermometers are inserted in here. So you can imagine that some thermometers are inserted in here. The thermometers record the temperature at this precise value. At let's say at 1 centimeter, at 2 centimeter, you record the temperature. So you have a temperature distribution along this rod. Okay, so you are trying to get if you heat it up at this end, how the temperature is distributed. Okay, and these thermometers that you have, these thermometers also have a least count, let's say, that is the a minimum temperature difference that this thermometer is sensitive to, and that gives you kind of a measure of this sigma, okay, that is related to the sigma. And how do you take these measurements? So you repeat this experiment a number of times, and at each point you take the average of those temperatures, okay, and then you also get the sigma 1 sigma 2 as well. So you do a number of measurement at this point, a number of measurement at this point, and this y1 basically reflects the average of those measurements. uh, so due to the central limit theorem, it tells you that if you average out a large number of data from which are distributed identically, then it is supposed to behave like a Gaussian. Okay, so this central value, this y1 and this sigma 1, they can be thought to be the Gaussian mean and the Gaussian standard deviation of the value of the temperature at this point. Okay, so that is the crucial assumption. So at this particular point, you assume that whatever quantity you are measuring, since you are measuring it by taking a large number of average, you expect that your central limit theorem will hold sacred at that point. And so at this particular point, the random value that you are measuring for this y, let's say, and that can be thought to be distributed as a Gaussian distribution, okay, with mean at y1 and this at sigma 1. All right. Okay. So now what we do is that we try to plot this thing. So suppose this is your x, and this is your y, and at different values of so suppose this is at x equals x1, and you denote the data as, so this reflects y1 plus minus sigma 1. Okay, so this is the data with the error bar. All right, and then at x2 you have another similar, and then at x3 uh, you have another, and you get the idea basically. So you have different values such with the error bars at different points. Now suppose somebody told you that y depends, uh, like as a functional dependence, the y depends on x as follows. So basically y of x is, let's say, theta 1 x plus theta 2 x squared. Suppose there are only two thetas, only theta 1 and theta 2. Okay, and in general is basically y x theta. Okay? I mean, there can be more general, more complicated dependence, but let's say the dependence is like this. These are unknown parameters that you want to fit. Okay, so these are my unknown parameters. Now remember, if you tweak this theta 1 and theta 2, then the functional form will change of this yx, and there can be different yx depending on the values of theta 1 and theta 2. So you have to basically figure out what is the value of theta 1 and theta 2 for which the functional form or the plot of yx is such that it describes the data to the best extent possible. Okay, so this is the kind of the best fit yx. Okay, so basically this is yx with chosen values of theta that I call the that is that I call the maximum likelihood estimate of theta, And if I plug in these values of theta into this functional form, I get the best fit. Now, the method of least square is just a systematic way uh, of how we obtain these best fit values of theta 1 and theta 2. So hopefully the statement of the problem is clear to you. Okay. So now, uh, to see that, let us figure out that how these things are distributed. Okay. So so these are kind of n independent measurements, right? All these yellow points are n independent measurements. Okay. So these are n independent measurements of y. Okay. And since they are n independent measurements of y, okay, then suppose the true value of uh, of this mean that we do not know would be, let's say, lambda 1, lambda 2, lambda 3, and lambda n, so on. So suppose the true uh, values of the mean at x1, x2, blah blah blah, uh, would be lambda 1, lambda 2, and so on. So which will be obtained by this. So if we knew the this functional form with the true values of theta, I could calculate this lambda 1 by just plugging in the value of x1 and plugging in the true value of theta. So this lambda 1 is basically the actual function, this y at x1, and then the theta true, the true value of theta that we never know. Okay, so let me write it down. So we don't know this this we are trying to estimate. Okay, not a true value but an estimate for that. This is the actual value. So if we knew the true value of theta, then at just by plugging x equals to x1, I could find out that what is the true mean of this. Okay. Now assuming that those are Gaussian, they are distributed in a Gaussian way, then the probability distribution to find the value between, let's say, so to find the value y1 where the true mean is lambda 1 will be given by, so 1 by square root of 2 by sigma 1 square, then e to the power minus y1 minus lambda 1. By the way, of course, this lambda 1 is a function of theta, right? So because lambda 1 depends on theta as well. Okay, so lambda 1 whole square divided by 2 sigma 1 square. So this is the probability, or rather the probability density that we find y1 at the value that we observe. Okay. Now we have actually observed this y1, y2, blah 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 up to yn. So what is the combined PDF for that? Since these are independent measurement, so the combined PDF for all these measurements will be given by this. So this G of y1 uh, up to yn, okay, when the lambda 1 up to lambda n are the true means of that, and then sigma 1 square up to sigma n square are the standard deviations, and that would be given by the product of all the individual distributions. So this is I percent 1 by square root of 2 pi sigma I square e to the power minus um, yi minus lambda I whole square divided by 2 sigma I square. Okay, so this is the whole distribution. Okay.
Sir,
Yes.
can you repeat again what you define G?
So G is the combined probability of finding all these values as they are.
Okay, sir.
Okay, the
So
combined.
it also takes into account the sigmas.
Yes, because the Gaussian distribution accounts for the sigmas. Okay,
Okay,
so we take the estimated sigmas or whatever sigmas we get as to be the sigmas, okay,
okay,
of the distribution. Like how uncertain this can be. Okay.
okay.
So all right. Uh, okay. Now, so this is my roughly the probability. Then my log likelihood function will be just the logarithm of this distribution, if you remember this thing. So the if I go say log of this likelihood function, if you remember, so it's basically logarithm of this. So logarithm of this quantity is basically constant. It does not affect my minimization. So I only keep this part, and the product becomes summation. So this is minus of this is I equals 1 to n, and then this is yi minus this lambda I, as I told you, is basically lambda at xi, or rather y at xi, I should write. Let's say uh, y at xi, and theta, this whole square, divided by sigma I square. Now, ideally, I should maximize this log likelihood. So, I mean, instead of that, I can choose to define, because this really looks like the chi-square function. So this is the average minus the true mean divided by the sigma square. So I define a chi-square function. Okay, and this should be equals to summation over I equals 1 to n. Uh, then I this is yi minus y xi theta whole square by sigma square. So instead of maximizing the log likelihood, I can choose to minimize the chi-square function, which will have the same effect as maximizing the likelihood because of the negative sign in front. All right, so I can choose to minimize it. Okay, so so we can minimize uh, this chi-square theta, and and obtain our uh, estimate for the unknown parameters theta. So which we denote by theta least square estimate. Okay. So you minimize this with respect to theta, and then you get the best value of the estimate. Okay. Best value. So that's why it's called the least square, because you are minimizing this thing. So when it is the least, then you are taking the values of the parameters to be your best fit value. So this is the least square method theoretically. All right. Now, if these things are not independent, if these measurements are not independent, but they are correlated, but if we happen to know the correlation as well, then still we can define the chi-square as a straightforward generalization of this. Hold on a moment, I have to take this call. All right. So, uh, okay. Now, if they are correlated, then we can define the chi-square in a similar fashion. So, this is the chi-square theta in the case of correlated measurement, that is ij equals 1 to n. Then this is yi minus y xi given theta. Then the correlation matrix inverse ij, and then the jth component. You can easily check that this definition uh, kind of reduces to this one in the limit when this B inverse is a diagonal matrix, that is in the limit that there are no correlation between this observed quantities, this between y and 1 yj. This is a diagonal matrix, and then it reduces to this form. All right. So, in the case of correlated observations, you can try to minimize this to obtain your results. Okay. So this is basically the methodology of least square. Usually, you do need computer programming to actually perform this, but there are some simpler situations where you can do something by hand and you can get some analytic expressions. All right. So. So one of the special case, so I will write down this thing, special case, is the linear least square fit. Now, the linear least square fit is useful when your y, the functional dependence of y on x, is linear on theta. So this functional, the functional dependence on theta is linear. So that means, what I mean is that, suppose I have m number of unknown thetas, then I can write it as ajx times theta j. Okay. So notice a very important thing here. So it depends linearly on theta I, but the coefficient uh, of this theta i's, or rather theta i's are the coefficients, but the things that theta i's are multiplied with, they do not need to be linear in x. So they do not uh, need to be linear in x. Okay. The only thing we need is that all these ajx are linearly independent. So uh, all these ajx are linearly independent. Okay. So to give you a certain feeling on why I say these things, you go back to the example that I gave you. Suppose the yx has this form, theta 1x plus theta 2x square. See, the important bit is that it depends linearly on theta 1 and theta 2, on the first power of theta 1 and theta 2. It does not depend on theta 1 square or theta 2 square or any more complicated one. But things that they are multiplied with the x functions, right? This is x square and this is x. You see that theta 2 is multiplied with x square. So that is fine. That is absolutely fine. As long as the functional dependence on the parameters are linear in themselves, we do not care anymore. Okay, so that then if the functional dependence on the parameters are of linear in nature, then whatever conclusion that I draw from this linear least square fit will hold true. Okay, that is what I mean. And the second requirement that I have is that the functions that this theta 1 and theta 2 are multiplied with should be linearly independent. Okay. Suppose instead of the so suppose the first function is x and the second function is, instead of x square, it is, let's say, 3x. Notice that this x and 3x are not linearly independent. So then there is no point of treating this theta 1 and theta 2 as independent parameters anymore, because you can just plug it in. So you can basically redistribute these x's, and then you have a function which is theta 1 plus 3 theta 2 times x. So then why not you call this theta 1 plus 3 theta 2, and you call it a new parameter, that is theta prime. So there is no there is no two independent parameters. You essentially have one parameters. So that is the thing I mean when I say that all these multiplying things should be linearly independent. Otherwise, these m number of theta j's, independent theta j's, will lose meaning. So we will need m number of independent theta j's only when I have a linearly independent set of this ajx. All right. So suppose the linear least square fit is applicable to the case when my the functional form of the thing that I'm going to measure and the parametric dependence of that thing is linear. So then, if I want to compute in this special case, if I want to compute this thing called, let's say, lambda I, which is essentially the value of y at xi theoretically given theta, okay, and that is just summation over j equals 1 to m, then aj at xi times theta j. Okay, so that is the thing I get, and I want to be a bit fancy, so I write it in this form. So this is summation over uh, j equals 1 to m, and then there is aij, uh, then this is theta j. All right. So that is my lambda I. Okay. And actually, you know what? On a second thought, I would like to change the name of the index uh, of this J here. Okay, because in my notes I did in this way, but now I think it's a better idea that I reserve a thing. Let's say alpha equals 1 to m. This is a alpha x theta alpha. To remind myself that this alpha index essentially tells you the number of theta parameters that you have in your theory. And Roman index I essentially gives you the number of measurements that you have done on Y. And these two numbers may be different. You see, I am summing over M here, and I am summing over capital N there. Okay. So I just reserve this thing. So I call this alpha. Sorry for this thing. And I call this is A. Nope. I was fine. So this is AI alpha theta alpha. Great.
Sir,
Yes.
so when we are writing xi, isn't it for a particular point?
Yes.
So it is not counting the number of in measurements we are doing, right?
Yes, when you sum over I, you are doing it for every I. You are calculating lambda I for I equals 1 to n.
Yeah,
So,
that is for different measurements, right?
I mean, all these points are different measurements, all these
Yes.
points.
But
So,
at a particular point, we are doing many measurements and getting sigma 1 and lambda 1.
no, you are getting y1 and sigma 1 by doing many measurements. So, you are doing many measurements at a single point so that you can be confident that this distribution will be Gaussian, or you can describe this by a Gaussian distribution. But your whole experiment, the definition of an experiment is a set of all these measurements.
Okay.
Okay. All right. So, uh, All right. So this is how I write my. So I define a matrix called AI alpha. So the matrix element is defined as basically AI alpha is equals to A alpha at xi. So this is my definition of AI alpha. Notice that it is not necessarily a square matrix. Okay. So in the left hand side you have a column matrix which has n elements, capital N elements, and on the right hand side you have a theta matrix, like which is a column matrix which has small m elements as well. So this is, in all probability, this is a non-square matrix. So keep that in mind, and when you uh, do gymnastics with this A matrix, just keep that in mind. Okay. So now, from this definition here, or the other, let's say the more general definition here. So this is chi-square is basically a combination of three matrices. So this is a row matrix. Okay. So what I can say, so these are my lambda i's, right? So this is my lambda I, this is my lambda j. So what we could write from there is that the chi-square would be given by y, the y vector, minus the measured y vector, basically the lambda vector, okay, transpose, then v inverse, and then y minus lambda vector. So this is essentially the same as this thing. Okay. So this is the row matrix, and this is the column matrix, and this is the square matrix in between. So you have this in matrix notation, so that things are a bit easier to handle. All right. So now this lambda vector is basically A times theta. So you notice this equation. This can be written as, this is A times the theta vector. So A is a non-square matrix, and that's the theta vector. Those are vectors of different dimensionality. Be careful about that. So this I can write as y minus A times theta transpose V inverse y minus A times theta. Okay. So this is the y. So remember that y is essentially this y1 up to yn transpose, rather. This is the vector of measured values. This is the important thing. So this is the vector of measured values. Okay. And lambda, which is equivalent to lambda 1 to n. This is the vector of the predicted values. Okay. So of course these lambdas will depend on theta, and they basically depends on this theta vector. Not an issue. Okay. So to actually find the minimum of this chi-square, you have to minimize this. Now theta has different components, theta 1, theta 2, up to theta m. So basically you minimize it with respect to each and every theta. That means you do it component by component, which is in essence uh, basically asking that the gradient of this chi-square is 0. So if you construct a gradient operator, so the gradient operator with respect to theta, basically on operating on x square, this should be equals to 0. Basically that gives you the individual theta operations equals to 0. Okay. If somebody is shaky about that, if you are not from a physics background, take help from any of the physics batchmates from here. It is very simple if you know partial derivative, but you will get help from your physics friends here. So basically I have to calculate the gradient of this thing here, and I have already calculated that. So I will ask you to check that if this two holds true. So this is minus 2, then A transpose V inverse Y vector, and minus uh, A transpose V inverse A theta, that should be equals to 0. So this basically enables me to calculate the best fit value of theta. Okay. So, or the best fit value, by best fit value I mean here is the least square estimate of theta. So this enables us to calculate the least square estimate of theta. Okay. And what will be the least square estimate? Assuming that this matrix is non-singular, so that you can safely take the inverse of that. Okay. So since this is 0, that means if you uh, shuffle that equation a bit, then you end up with A transpose V inverse A times theta vector should be equals to A transpose V inverse Y. Now, to get your theta vector, or rather theta least square estimate, I would say, you basically multiply by the inverse of this matrix from the left and multiply it here. So that is A transpose V inverse. Uh, no, A transpose V inverse A inverse uh, A transpose V inverse Y. Okay. Now, so this is my least square estimate for this thing, and I notice that it looks like some matrix B times Y, okay, where I have this whole thing up to Y as my B. So theta ls is just a transform variable uh, compared to Y. Okay, compared to this Y, whatever we had. Okay. Now, how can I get the covariance of these least square estimates then? So this is the my least square estimate. This is my central values. But remember, I told you that whenever you make estimate, you also should tell you how robust is that estimate. That means under repetition of this experiment, this whole experiment, I mean, how reproducible is your are your values in here. Okay. So for to do that, you need to calculate the covariance matrix in this theta basis. Okay, and if you transform your theta from this y by a linear transformation, that is b, then you already know the covariance matrix in terms of this y, that was v. Okay, so the covariance matrix was in terms of y is the covariance matrix that you use to construct chi-square at the first place. Then the covariance matrix in this basis, this theta hat ls, which I call u, should be related to the covariance matrix in the y basis v by a similarity transformation. Okay, it is b v b transpose. Okay, so that is my thing. Okay, now if you substitute all these things here carefully, then you should have let me do it carefully. A transpose V inverse A whole inverse, then A transpose V inverse. times V times B transpose, right? So first you do A transpose B inverse this whole transpose times uh, the A transpose B inverse A whole thing inverse. This whole thing is transposed. Okay. You can easily see that, for example, these two things combine to give you the identity matrix. Okay, so there is nothing in here. Okay, and I ask you to simplify these things. So simplify these algebra and cancel out all these things, and at the end of the day, you should find that the whole thing is equals to A transpose V inverse A, the inverse of that. Okay. Now, basically, if you now calculate the U inverse, then it is A transpose V inverse A. Okay, from here. All right. So, if you notice carefully, the way the chi-square is defined earlier, so chi-square is this, right, in terms of A. You see where A transpose V inverse A comes from. So A transpose will come from here, V inverse comes from here, and A comes from here. And basically, when you multiply the term that is quadratic in theta, so this is A theta transpose, then V inverse, then A theta. From that term, I get a term bilinear in theta. So kind of the term that is bilinear in theta contains the U inverse. Okay. So quite naturally, this U inverse can be alternatively expressed as, if you calculate this carefully, half uh, del 2 chi square del theta alpha del theta beta, okay, at theta equals theta ls, then you will get the alpha beta element of the U inverse as well. See, so this is the thing. Okay. So this U inverse alpha beta equals half del 2 chi square. So you can explicitly check. So this explicitly check from the expression for chi square theta. Okay. So if you do this explicitly, then you will see that this is precisely equals to this. Okay, once you do everything correctly. Now, I guess it is a good time to remind you about this RCF inequality that we discussed in the previous class. I told you that the variance of the maximum likelihood parameter, or rather the covariance matrix of the maximum likelihood parameter. So if you remember correctly, so if you from the RCF inequality, the approximate version, you had the V inverse, the correlation matrix, the let's say alpha beta, was essentially equals to minus of del 2 ln L divided by del theta alpha del theta beta, evaluated at uh, theta, or rather theta equals theta hat. I mean, at the estimated value, if you evaluate that, then you get the covariance matrix. And we checked it explicitly from a known example, which was the example of the exponential decay. Okay, so next we checked it explicitly that this actually holds. Okay. Now you compare these two, and you notice that these two are the same equations. because log likelihood is basically minus half chi square. If you see here, so log likelihood is minus half times the chi square function. And so if I say this, then I basically mean this as well. So this is also consistent with the RCF inequality. So this is consistent with the RCF inequality or the RCF bound. Now, the same question arises that in a graphical method, how can we obtain the mm, the chi-square, basically the 1 sigma value for the 1 sigma value for the least square best fit value for parameters. So what I mean is that suppose you have a single parameter, let's say this is theta, and you are plotting chi-square theta in here. The theory tells you that it should be minimum at some point. Okay. And that minimum point you identify and mark it with this is my best fit value from the least square fit. Now you have to also tell that how reproducible your result is. That is, if someone repeats the experiment again and again, and that person will likely to have a different set of values for y1, y2 up to yn, and for that person this least square estimate will be different. Now how different can it be? You can get a sense of that by quoting the statistical error involved in this thing. Now how to obtain the statistical error? For that, what you notice is this following. So if this is my chi-square theta, and if you again expand this chi-square theta in a Taylor series, suppose I have one parameter, so this is chi-square theta, and then this is the chi-square theta chi-square at theta ls plus del chi-square del theta uh, times theta minus theta ls. Okay, but this thing is 0, right? Because I am minimizing chi-square, so that thing vanishes out. Okay, and then plus I have del chi-square del theta 2. Okay, evaluated at theta equals theta ls. This is also theta equals theta ls. Okay. And then theta minus theta ls whole square by factorial 2. All right. So now from the idea that I presented here, del chi square del theta 2 half multiplied. This is just the inverse of the correlation matrix. In the case I have single variable, this is 1 by sigma square. So this is basically 1 by sigma square if I am only considering uh, if I am only considering this a single parameter theta. Okay, so this thing, uh, this including the half factor is just 1 by sigma theta ls estimate square, okay, times theta minus theta ls whole square. This is already here. Now the first term is again chi-square mean. The second term, so in the neighborhood of the least square estimate for theta, the chi-square function behaves like this. So in the neighborhood of this, the chi-square function basically behaves like this. Now again, I notice that if I go to a special point, that if I move from theta ls base fit by one standard deviation, oops, sigma theta ls by one standard deviation, that is theta minus theta ls as sigma ls square, and you substitute it here, then what you obtain is that chi square theta at that point, at this point, is basically chi square mean plus 1. So this is from this, right? So if this is your chi-square mean, and you move to a point such that your chi-square mean gets increases by 1 unit, so this is chi mean square plus 1, then whatever value of theta that you hit here around this theta ls will be the 1 sigma bound for your. So this is theta ls plus sigma theta ls hat, and this is theta ls minus sigma theta ls. Okay. So you have to look for a contour for which,
Sir,
yeah,
so the chi-square theta will be chi-square mean plus half or 1?
mean
I mean,
plus 1,
okay,
because the factorial 2 is taken into account here.
okay, okay.
So easy way to remember, log for log likelihood it was half, but that half factor has been absorbed in the definition of chi-square. So this is
Okay,
the
sir.
half factor. So that's why once you go to 1 sigma limit, you go to chi-square mean plus 1. Okay. And if you go to 2 sigma, then you go to chi-square mean plus 4. Okay. Because so basically, if you go to n sigma, the general rule is you go to like chi mean square plus n square, okay, for n sigma. Because in this formula, in the neighborhood formula, you can actually check. So if you, instead of going 1 sigma, if you are going to, let's say, n sigma, then it will be n square. Yes, I mean plus n square, because of this obvious thing. Okay. So
Sir, when we are going n sigma uh, from the theta ls, so we don't consider higher terms.
no, you are assuming that you are sufficiently close to theta ls.
Okay,
Okay.
sir.
If you have to consider higher term, then your fit is not good, and you should discard the hypothesis point.
Okay, sir. Okay, sir.
All right. So, and of course, you do not go very far from this theta. I mean, you cannot apply this for n equals 100, but for n sufficiently small, let's say 1, 2, 3, it will work. Okay. All right. So now it's quite obviously for a multiple variable fit. So instead of theta, only theta, if you have theta 1 and theta 2, it's like a three-dimensional plot, and you will mark the point at which chi-square is minimum. So this is the point you mark with theta 1 hat and theta 2 hat ls. So this is your best fit point from maximum likelihood analysis. This corresponds to chi-square mean. And if you draw a contour around it, uh, the contour is usually elliptical because of the functional form. So this is the contour in the theta 1 theta 2 plane where chi-square is raised by 1 unit. Okay. Then this is the your 1 sigma region, okay, or the, so this is the 1 sigma region. Okay. And if you want a 2 sigma region, you go to chi-square mean plus 4. So if this contour is your chi-square mean plus 4, then this is a 2 sigma region. Okay. This will be a 2 sigma region in here. All right. So in a nutshell, this is it. Okay. So how you, this is how you mm, extract the parameters when your measurements are in a way that the measurements, the measured values are itself function of a random variable and the parameter. The random variables on which these measured values depend on are somehow can be well measured, like the position at which you are measuring temperatures, they can be well measured, let's say. Or in the case of particle physics, the energy bin that you are measuring your number of number of events, these energy beam can be very precisely located. You assume that, and then you can do a chi-square analysis of this sort to get the best fit value of your desired parameters. Okay, so this is the method. I think so. Today was a usual 1 hour lecture. Today I will stop here, and the next day I will probably take two more classes and then get it done with. And now let me know if you have more questions in here. Any questions? Okay, in that case, I will stop